Welcome students. In today's video lecture, we'll be talking about the GeigerMullerCounter. This is another kind of nuclear particle detector. So what is it basically? It's a nuclear detector which is used to detect different types of nuclear radiations. So this GeigerMullerCounter is a very versatile device and which is useful for detecting and measuring the energies of alpha, beta, gamma and even X-rays. It's also sufficiently sensitive to detect individual alpha and beta particles, and hence it is very widely used. So it's a gas field detector, as we talked about, which based on the phenomenon of ionization. A particle incident or entering the detector, it causes ionization in a gas which produces a pulse, electric pulse, which can be detected or measured. So this is a simple picture of a GM counter. So as you can see here, this is the high voltage device plus the counting part, and this is the tube, GeigerMuller tube, or this whole combination is called the GeigerMuller counter. So let's look into the construction of a GeigerMuller counter. So these are two kinds of GeigerMuller counters. So as I told you, it consists of two parts: the tube. This is the tube here, and this is one design, and this is the another design, and the counter with the power supply. Counter means the electronic circuitry or the electronic device which is used to count the pulses produced by the tube. That is the counter. As a whole, this whole thing with the counter and the tube will be called the Geiger-Müller counter. So the first one, it's a kind of a metallic cylinder which is a cylindrical cathode which is enclosed in a glass envelope, and a fine tungsten wire. This is the tungsten wire which serves as the anode. The rays or the particles to be detected, they enter the Geiger-Müller tube through the glass envelope. However, a different design is used for less energetic particles, beta particles, and for alpha particles whose penetration power is a bit less. So for this kind, for detecting these particles, less energetic beta particles, or for alpha particles which have lesser penetration power, a N window type of GM counter, GM tube is used, where at one end of the tube there is a window of thin mica. There is a mica window which allows the particle to enter. In this case, the anode wire, which is insulated from this metallic chamber, which is the cathode, it's a thin wire again, but it is not throughout the tube. It's extended almost to 3/4 of the length of the tube. So this is N window type, and this is with a glass envelope. So the GeigerMüller tube is a hollow metallic cylinder which serves as the cathode. This is the one that we are talking about. A thin axial tungsten wire, radius of around 0.1 millimeter, and insulated from the chamber. It serves as the anode. The tube is filled with a gas, usually helium, argon, or neon, at low pressure, around 10 centimeter of mercury, mixed with a volatile compound like ethyl alcohol, which serves as the quenching agent in the ratio 10:1. Also, the quenching agent, depending upon the design of the GM counter, can be a halogen like chlorine, mixed with the halogen can be chlorine or bromine. In some tubes, as I told you, neon gas mixed with traces of halogen and bromine are used. A high potential difference of about 1000 to 3000 volt applied between the electrodes for the first kind of tubes, and comparatively lesser voltage 300 to 400 volt for the second kind of tube. The first kind of tube with the glass envelope, and the second kind of tube, the end window. So depending upon the purpose of the GM counter, different designs are used and optimizations are used. So in one, we are talking about helium and argon at low pressure mixed with ethyl alcohol, and the other neon with traces of even neon or argon traces using traces of bromine, or it can be chlorine also in some others are used. So these are different variations of the design of a GM counter. The gas should be free from impurities to avoid spurious pulses. We'll talk more about it. So how does it work? So what happens? The particle enters the chamber and causes ionization. This can be either directly or indirectly. Directly means the particles entering the chamber from the source, knocking off electrons from the atomic orbits. So this is direct ionization. Other way around, the electrons which are ejected from the primary ionization, as they travel through the gas inside the chamber, these electrons also are energetic enough and they can knock off electrons. Secondary ionization. The electrons produced by primary ionization, as we talked about, move rapidly under the influence of the strong electric field. So as a result of the ionization, positive ions and free electrons are produced. Now, the ions being comparatively massive compared to the electrons, they move slowly compared to the electrons. Now, because of the structure of the electric field, it's radial in nature, because this is the cathode and this is the thin anode. So these are the field lines. So near the anode, the density of the field lines is very high, and hence the electric field being radial, it's very strong near the anode. So any free electrons or the electrons which are produced because of the ionization due to the incident particle, these electrons, as they approach the anode, they get accelerated very rapidly. So because of this rapid acceleration, they gain sufficient energy to cause further ionization, and this process it multiplies, and the process is cumulative. As a result, what happens? A large avalanche of electrons is produced. Also, another important event takes place. What happens? Apart from the electrons which are causing ionization, primary electrons produces secondary electrons. The secondary electrons also produces ionization. Avalanche is produced. Avalanche of electrons is produced. Some of the electrons, what happens? They collide with the gaseous atoms and they don't have that much energy to produce ionization. So what they can do? They can simply excite the gaseous atoms. So these excited atoms, they return to their normal state by emitting light photons. Now, these photons, they are not charged. They may be energetic gamma photons. So they are not charged. So they are not under the influence of the electric field. So they can spread throughout the GM tube. And these photons again can produce ionization at some other corner of the GM tube. As a result, what happens? A single particle entering the GM tube can trigger an avalanche, and the avalanche it spreads rapidly throughout the entire volume of the tube within a short time of around 1 microsecond. So within this time, amplifications as high as 10 to the power 8 is reached. That means from 1 electron, 10 to the power 1 electron being produced in a primary ionization, 10 to the power 8 electrons can be produced. So this total number of ions produced is now independent of the initial number of ions produced by the or formed by the entering particle. So multiple avalanches leading to Geiger ditches throughout the tube. We call it the Geiger ditches. So dense ion electron cloud is produced. Now the light electrons, they are collected rapidly by the anode. They are light, they can move fast, so they are collected rapidly by the anode. However, the heavy ions, they form a space charge sheet, reducing the field. So it shields the electric field. The positively charged ions, they're moving towards the cathode, but then as because most of the ionization is produced near about the radial part or otherwise, they take time to slowly move toward the cathode. As they reach the cathode, what happens? They get neutralized. But as they are moving slowly, what happens? They form a space charge and it shields the electric field. So the effective electric field reduces, stopping the discharge. So what happens? As I said, the size of the pulse produced is independent of the type and energy of the incident radiation. Whatever be, because the electric field is strong enough, the potential difference applied is very high. Whatever be the particle or the energy of the particle entering the chamber, as long as it can trigger an avalanche, the size of the finally produced pulse, it is independent of the type and energy of the incident radiation. So what happens? There is something called the date time. What we said, the ions being slow moving, they form a space charge which becomes dense enough to cancel the electric field around the anode. As a result, for some time, ionization stops. So, the positive ions need to reach the cathode so that they get neutralized and the electric field builds up again, and then only ionization can start again. This period during which ionization remains suspended is called the date time. So another aspect is there which is called the recovery time. As the ion sheet slowly moves towards the cathode, they get neutralized and slowly the electric field builds up. And there is a time between the ionization stopping and the electric field attain its final strength. In between, pulses of reduced sizes are recorded for some time. So this time is called the recovery time. From the point when the ionization stops till the electric field reaches its final strength. So the date time plus the recovery time gives the resolving time of the counter. Resolving time means the time in which after recording an event, the GM counter is again ready to record the next event. That is the recovery time. So that is the resolving time. The date time, recovery time and resolving time. These are some parameters associated with a GM counter which needs to be understood. But the important point here is when a particle enters the chamber or the GM tube, the magnitude of the pulse produced is independent of the energy and the nature of the ionizing particle. So this current pulse that is produced, it produces a corresponding voltage pulse across the resistance connected in series with it. This voltage pulse is fed to a pulse amplifier through a capacitor. As you can see in the construction part we showed, sorry for this, it passes through a capacitor, it is amplified, the pulse is amplified, and finally it is counted. So the scaler or the counter, it counts the arrival of each individual pulse separately, and it can exactly give the number of particles entering the GM counter in a particular time interval. Now, because the magnitude of the pulse produced does not depend upon the nature or energy of the entering particle, a GM counter cannot distinguish between the kind of particle that is entering the chamber. That is, whether it is an alpha particle or a beta particle or otherwise. However, there is a way out. The particles can be distinguished by finding what absorber placed in their path will prevent them from entering the GM tube. This is an indirect way of distinguishing the kind of particle entering the GM counter. Now, there is a problem associated with GM counter which needs to be avoided: multiple pulsing or spurious pulses, and hence quenching, which can be internal or external. So what is the spurious pulses? Now, the GM counter or the tube must produce a single pulse because of the entry of a single particle. It should not give any spurious pulses, and it should recover quickly to record the next entering particle. However, it so happens that some of the ions, on reaching the cathode, they neutralize in the cathode by taking an electron. After neutralization, they remain in an excited state. And these ions or neutralized atoms, which can be argon atoms of the argon gases, they come down to the ground state by emitting photons. And these photons, they trigger an avalanche. So if this happens, multiple pulsing occurs, or these are spurious pulses. A particle entering this chamber, it triggers a pulse, but then again the ions being neutralized in the cathode, they also can trigger a pulse. So these pulses or the spurious pulses, they needs to be avoided. How they can be avoided? By mixing a polyatomic or diatomic gas such as bromine or chlorine in the tube. That's what we are calling the quenching agent. So mixing this with the gas in the tube is internal quenching, or externally it can be done with the help of circuitry. Here we are talking about internal quenching. So what happens is the positive argon ions, when they are moving slowly towards the cathode, in the presence of the quenching agent, they will collide with the bromine molecules. Suppose bromine is the quenching agent, and they transfer their charge to the bromine molecules. Now, no longer argon ions reach the cathode, as because they transfer their charge to the bromine molecules. The bromine molecular ions now reach the cathode, and by accepting electrons from the cathode, they neutralize. However, these bromine molecular ions, or the quenching ions of the quenching agent, on reaching the cathode and getting neutralized, even if they are in an excited state, they don't come down to the ground state by emitting photons like in the case of the argon ions. But what they do, the excited bromine molecules, they lose their excitation energy by breaking up into bromine atoms. It's a diatomic gas, so they lose their energy by dissociation into bromine atoms and not by photon emission. And hence, in the presence of the quenching agent, no spurious pulses are produced. And in course of time, these bromine atoms, they recombine to form bromine molecules again. Thus, the presence of the quenching agent, it quenches the discharge, and the tube can be ready to receive the next particle within a time of around 10 to the power minus 4 seconds. So this is what is quenching. So the presence of quenching is a process in which the spurious pulses are avoided or which are removed, and the agent which serves this purpose, thus the quenching is called the quenching agent. Now let's look into the characteristics of a GM counter. It's important to operate a GM counter at a correct potential difference. So the characteristic of a GM counter is nothing but a plot of the counting rate against the potential difference applied between the anode and the cathode. The characteristic looks something like this. For low potential difference, only the most energetic particles can produce detectable pulses. Now as the potential difference, applied potential difference is increased, the count rate obviously it increases. In this region, the magnitude of the pulse it depends upon the energy of the entering particle, and only those particles are recorded which gives detectable pulses. However, beyond a threshold, there is a range of potential difference. This is one threshold that we are talking about. There is a range of potential difference in which the count rate is almost constant. This region is known as the operating region or the plateau region. Plateau region. In this region, all pulses are of the same magnitude and every entering particle is recorded. So this is the range of potential difference in which a GM counter must be operated. For a halogen quenched GM tube, this range is about 400 to 500 volts. And this is for the the glass enveloped GM tube is between 1200 to 1500 volts. So the GM counter operating voltage is ideally fixed somewhere in the middle of the plateau region, so that even if there is fluctuation in the voltage, it doesn't go into this region and the continuous discharge region. So what happens if the potential difference becomes very high? The GM counter or the GM tube goes into a continuous discharge region. Means in this region, because of the electric field itself, electron ion pairs are produced without any incident particle even. The counter can show a pulse because the electric field is so strong. It itself causes pulse of the electrons from the orbits. So let's look into the advantages and disadvantages of a GM counter. Sorry, this part. GM counter is very simple device. It's versatile and is easy to build. This is the advantage. And it can also detect different kinds of particles of different energies. However, disadvantage is it has comparatively high dead time, 200 to 400 microseconds. So it can't detect particles emitted with high rate. So if a particle is emitted within its dead time, it won't be able to detect two particles which is within the period of the dead time of the GM counter. It won't be able to detect it as separate particles. That means high sources having high rates of emissions, it will be difficult to use a GM counter. Also, it cannot distinguish between the energy of the incoming particles, that is, the pulse height is independent of the energy of the incident particle. So these are primary disadvantages of a GM counter. However, seeing its simplicity, seeing its versatility, GM counter is very popularly used for different purposes, for detection of radioisotopes, to study the activity of different sources. So as I told you, this pulse height will depend upon it's independent of the energy, but we can measure the activity of different sources using the GM counter. So that is all about the GM counter. Thanks for your listening.